Today what we're going to do is we're going to learn about logarithmic functions and models. So logarithms are used in areas like physics and finance and economics, and the goal of this section is for us to learn applications of logarithms. And we'll actually learn that logarithms and exponential functions are inverses of each other. All right, so let's start out with a definition. The logarithm, that's an O, the logarithm of x with base a, written as log of x base a, is the power to which a must be raised in order to get x. Mathematically, we say the log of x base a is equal to y if and only if a raised to the y equals x. Okay, so log of x base a equals y means a to the y, so your base raised to the right hand side is equal to the inside. Okay, now we have logarithm identities that you'll need to know, and you need to make sure that you are aware of this. Okay, the logarithm identity says suppose x and y are positive numbers, r is a real number, and suppose a and b are not equal to 1. Then the log of the product x times y base a is equal to log of x base a plus log of y base a. The log of x divided by y base a is equal to log of x base a minus log of y base a. Log of x to the r base a is equal to r log of x base a. So that exponent here can go on the outside of the logarithm. Log of a base a is equal to 1, and log of 1 base a is equal to 0. Log of 1 over x base a is equal to negative log of x base a. And then log of x base a is equal to the log of x base b divided by the log of a base b. So this allows us to change our base if we want to. Okay? Now, the logarithm, because we use it so much, the logarithm with base 10 is called the common logarithm. That is called the common logarithm. And it is written as log of x base 10 or just log of x with an understood that that's a 10. Okay? The logarithm with base e is called the natural logarithm. It's called the natural logarithm. And it is written as log of x base e or ln x. Okay? Now, logarithms and exponential functions are inverses of each other. Why is this true? Or let me provide a brief explanation. So log of a to the x base a is equal to x. So in other words, the power to which you raise a in order to get a to the x is actually x. Okay, so an example for this is log of 3 to the 8 base 3 is actually equal to 8, because in order to get 3 to the 8th, 3 has to be raised to the 8th. Okay, now a raised to the log of x base a is equal to x. So what this says is, it says raising a to the power to which it must be raised to get x actually yields x. An example here, 6 raised to the log of 7 base 6, that's just equal to 7. Okay? Now what we're going to do is go through an example. We're going to rewrite the following using the logarithm identities from the bottom of page 1. Part A says the log of 2/5 divided by 3. So the identity from page 1 that we are using is identity 2. So this is going to be equal to the log of 2 base 3 minus the log of 5 base 3. Okay, and that is a 5 here. Okay, awesome. Part B says we want to find the log of 50 base 50. Look back on page 1 and you can pause your video to find out which identity we're using. Okay, now you should see that we're using identity 4. So the log of 50 base 50 is actually equal to 1, since if we take our base 50 and raise it to the 1 here, we get 50. Okay? All right, awesome. Now, part C is a little bit more challenging. We have the log of 3 to the 5th divided by 7x base 2. So first things first, we're dividing. So we look back and we use identity 2. So that gives us the log of 3 to the 5th base 2 minus the log of 7x base 2. And we can simplify this further because you have 3 to the 5th here. So we can bring down the 5 in front of the logarithm using property 3 or identity 3. So you need to make sure you're familiar with your identities. You'll have lots of homework problems where you can go through and try or apply these identities. So you have 5 log of 3 base 2, and then notice that you now have a product 7 times x. So you go back and you use identity 1 for this portion. But be careful, because when you separate it, you now are subtracting 2 terms. So I'm going to put this in parentheses. So you'll have the log minus the quantity log of 7 base 2 plus log of x base 2. And now we distribute our negative. So we have 5 log of 3 base 2 minus log of 7 base 2 minus log of x base 2, and this is our final answer here. Okay, so there you have it. Now what we're going to do is we're going to evaluate an example or some problems that have the natural log involved. Okay, so example 2. Let's remove this a little bit. Zoom in. All right, we want to evaluate the natural log of e. The natural log of e is equal to 1, and you might be asking yourself, why is this? This is true since we know that ln can be rewritten as log base e of e, right? This e corresponds to this e, and ln corresponds to log base e, okay? Well, that has to equal 1, right? So that's true. And if we take our base e and raise it to the right-hand side of that equality, which is 1, notice that that's e, which is a true statement. So that's why the natural log of e is 1. The natural log of 1 is what? Pause the video and try this on your own. Now when you come back, that's equal to 0. Why? Because we can say that the log of 1 base e is equal to 0, since we know that e raised to the 0 equals 1. Okay? And then the natural log of 1/2 can be written as the natural log of 1 minus the natural log of 2. Remember, we're looking at the natural log of a quotient, so you're using property 2 or identity 2 from page 1 of your notes. And then the natural log of 1 in part B we found out was 0. So this just gives us negative natural log of 2. Okay? The change of base formula says the following. The log of A base B is equal to the log of A divided by the log of B. Notice that this is the common log because there's no base written, so it's an implied 10. Or we can write that as the natural log of A divided by the natural log of B. Now, the change of base formula is useful because if you're trying to enter logarithms into your calculator and you do not have a specific base, you can easily change the base using one of these. Okay, so let's look at some examples. So we want to evaluate using the change of base formula. Log of 5 base 2. It does not matter which one you use, this one or this one, whichever one makes you happy. Okay, so let's just rewrite this one using the common log. So log of 5, which is an understood base 10, divided by log of 2. And that's going to give us, when you enter it into your calculators, 2.32193. Now, part B, the log of 10 base 12, that's equal to, I'll use the natural log this time, it's equal to the natural log of 10 divided by the natural log of 12. And when you enter that into your calculators, you will get 0.92663. Okay? All right. So that's an application of the change of base formula. And now let's talk about a logarithmic function. A logarithmic function. A logarithmic function. So we've talked about logarithms. Now let's talk about a logarithmic function. The form of it is f of x equals log of x base a plus c, where a and c are constants with a greater than 0 and a not equal to 1. So your base cannot be negative, okay? And it cannot be 1, okay? Or you can have f of x is equal to a times the natural log of x plus c with a not equal to 0. Okay, so that's a logarithmic function. Now let's graph some logarithms. Okay, so for example 4, we want to graph the given function. We want to graph the given function. Okay, so we are graphing log of x base 5. So what will help us here is to remember the following. Remember that f of x equals log of x base 5 means the same thing as y is equal to log of x base 5. But by the starred property from the first page of our notes, remember that this means that when we take our base and raise it to the other side, we get this. So this means 5 raised to the y is actually equal to x. So now what we can do is we can choose various values for y and we can find out what the corresponding x is going to be. So that's what we want to do. So we can make a table. Okay? And let's choose y to be -2, -1, 0, and 1 so we can get a clear picture of what our graph will be, what the shape is going to be. So when y is -2, then x would be 5 to the -2nd, which is the same thing as 1 over 5 squared, or in other words, 1 over 25. Okay? So that's the corresponding x. Whenever y is -1, we get 5 raised to the -1, or either 1 over 5. Okay. whenever whenever y is 0, we have 5 to the 0, which is just 1. And then when y is 1, we get 5 raised to the 1, which is just 5. So now we can plot our points. We'll have the following. When y is -2, so when y is -2, our x value is 1/25. So that is about there. And then whenever y is -1, so when y is -1, we have that x is 1/5. And this is an exaggerated graph, right? So that's 1/5. Then whenever we have y is 0, when y is 0, x is going to be 1. So that's our x-intercept. It's 1. And then when y is equal to 1, when y is equal to 1, we get x is now 5. So when x is 1, or when y is 1, we get x is equal to 5. So that's x equals 5, which means this is our point. So we sketch the graph. Notice that it's never going to touch the y-axis, but it's going to get really, really close. And we sketch it. That's a sketch. All right, so that's the log of x base 5. Okay, now let's graph the log of x base 1/5. Okay, base 1/5. So remember, this means that y is equal to the log of x base 1/5, which means that 1/5 raised to the y is equal to x. Okay, same thing. You can choose values for y to find out what x is going to be. So let's choose y as 2, 1, 0, and -1. Now, whenever you substitute in y equals 2 here, you get 1/5 squared. So that's 1/5 squared, which is the same thing as 1/25. Then whenever you have y is 1, when y is 1, notice that you have 1/5. When y is 0, you have 1/5 to the 0, which is equal to 1. And then whenever you have y is -1, that's 1/5 to the -1, which is the same thing as 1/1/5, and that's equal to 5. Okay, so we plot our points, and whenever we have y is -1, whenever y is -1, we had x was 5. X was 5, so we're somewhere out here. Whenever y is 0, so whenever y is 0, x is 1. So we are now here. Whenever y is 1, so now y is 1. Whenever y is 1, we get 1/5. I'm going to put it here so we can plot our other point. Say that's 1/5. And then when y is 2, we'll have 1/25. Okay, so we're getting closer to the y-axis, but notice we're never going to touch it. So we have that as our graph. Okay, there you go. So we've learned how to graph given logarithms. Now let's look at another definition. Okay. Half-life. Half-life is the amount of time taken for the radioactivity of a specified isotope to fall to half its original amount or value. Half-life is the amount of time taken for radioactivity of a specified isotope to fall to half its original amount or value. Cool. Now let's look at example 5 to look at an example of half-life. Okay, so the amount of iodine 131 remaining in a sample that originally contained A grams is approximately C of T equals A times the quantity 0.9175 raised to the T, where T is time in days. Find the half-life to 2 decimal places. Okay, so we know, since we're finding the half-life, that C of T should be 1/2 of what our original amount was. Okay, it originally contained A grams, so this should be half of A. So we have 1/2 A is equal to A times the quantity 0.9175 raised to the T. Okay, now we want to find the half-life to 2 decimal places. So in other words, we want to find out what T is, which is what we're doing. Well, notice that both sides have an A, so you can cancel that or divide both sides by A. And then we get 1/2 is equal to 0.9175 raised to the T. We need to figure out how to get this T out of the exponent here. Okay, well, we learned properties of logarithms. That's what this section is all about. So we're going to apply the log to both sides of that equation. And you can either use the natural log or the common log. I'm just choosing to use the common log here. And then we can use our properties of logarithms, which tells us that this is log of 1 minus log of 2, and that's going to be equal to T times the log of 0.9175. And then, running out of room, so I'm going to go on the right side here, and notice that the log of 1, remember, is 0. Look at your properties and then use that fact to rewrite it. You will get that this is negative log of 2, and that's going to be equal to T times log of 0.9175. Now, we divide both sides by log of 0.9175, right? Because we want to isolate T. Well, that log is just a number, so we divide both sides by that. And then we get T is approximately 8.05 days. That is our answer. That's the half-life to 2 decimal places. Okay, now let's talk about the exponential decay model and half-life. An exponential decay function has the form Q of T equals Q naught e to the negative kt. Okay, Q naught, or Q sub 0, I say Q naught. Q naught, that's what we say in math. Q naught represents the value of Q at time t equals 0. And K is what's called the decay constant. The decay constant K and the half-life T sub h for Q are related by the following. The half-life T sub h times the decay constant is equal to the natural log of 2. And you'll need to remember this. You're going to have to apply that. Okay? So now let's go through an example together. Okay? All right, example 6. Zoom in just a little bit. There we go. Went right back. All right, example 6. Plutonium-239 is used as fuel for some nuclear reactors and also as the fissionable material in atomic bombs. It has a half-life of 24,400 years. How long would it take 10 grams of plutonium-239 to decay to 1 gram? Round your answer to 3 significant digits. Okay, so let Q of T be the amount left after T years. Okay? We want to find Q of T, which has the form Q naught E raised to the negative K times T. Okay, so we are dealing with an exponential decay function. Okay, first we have to find K. Okay, so we have to find K. All right, to find K, we're going to use the way we relate the half-life and the decay constant K. Well, that's equal to the natural log of 2 from the previous page, and we're given the half-life. We see that plutonium-239 has a half-life of 24,400 years. So T sub H, which is our half-life, is 24,400. We're going to multiply that by K, and that's going to be equal to the natural log of 2. Well, that means we divide both sides by 24,400. So K is going to be the natural log of 2 divided by 24,400. That will be approximately. Here we do not want to round our answer because we want our final answer to be very accurate. So we just write down what we get. Okay, enter that into your calculators. You get 0.00028408. Okay, so we found our K, we found our decay constant. Now, Q of T, we can use that to help us find our function. So Q of T is equal to Q naught E raised to the negative K, but hey, K we just found, so that's 0.000028408 times T. Okay, now Q of T, notice that how the question says how long would it take 10 grams of plutonium-239 to decay to 1 gram. So we know that we start out with 10 grams. Well, what we start out with, that's Q naught. So we know that Q naught is equal to, that's an equals, that equals 10 grams. And we want it to find out how long it's going to take that to decay to 1 gram. So we also know that Q of T itself is equal to 1 gram. Okay, so we substituting into, I'm going to call this line smiley face. So we get 1, because that's Q of T, is equal to 10, which is Q naught, we're substituting in here, E raised to the negative 0.0002, that's a 2, 8408 T. Okay, now we divide both sides by 10, we get 1/10 is equal to E raised to the negative 0.000028408t. All right, so now we're at the point where we want to isolate t. Well, it's stuck in the exponent. Remember, you have your logarithm properties, but the base here is e. So let's apply the natural log instead of the common log. So we get the natural log of 1/10 is equal to the natural log of e raised to the negative 0.000028408t. All right, so that gives us, running out of room, so I'm going to shrink this a little bit and move it up. So that gives us the natural log of 1 minus the natural log of 10. Natural log of 1, remember, is 0. So that's equal to negative 0.000028408t, because the natural log of e is just 1, right? Or they're inverses of each other. Natural log and e are inverses of each other. And remember, the natural log of e is 1. This is an exponent, so we can bring that down front. So we get times the natural log of e. Let's just write it. So the natural log of 1 is 0. So we get negative natural log of 10 is equal to negative 0.000028408t, because the natural log of e is just 1. We want to isolate t, so we divide both sides by this. Negative 0.0000, gosh, that's long, 28408. Awesome. Now, negative over negative is a positive. Substitute that into your calculators, and you will find out that that is 81,054, 81,054 point said to 3 significant digits, so 108, and that's going to give us t. All right, awesome. So that's how long it's going to take 10 grams of plutonium-239 to decay to 1 gram. Okay, now we talked about exponential decay. Let's also talk about exponential growth. So whenever we talked about exponential decay, we had half-time. Now when we talk about exponential growth, we're going to talk about doubling time. Okay, so an exponential growth function has the form q of t equals q naught e to the kt. Q naught represents the value of q at time t equals 0, and k is the growth constant. K is the growth constant. And the growth constant k and the doubling time t sub d for q are related by t sub d times k is equal to the natural log of 2. So notice that for exponential decay, the growth or the decay constant was negative, but here is positive because we're talking about exponential growth. And notice that this is how they're related. There being the doubling time and your growth constant. They're related by multiplying them, that's equal to ln 2. So now let's look at an example where we apply it. Okay, it's the name of the game. We talk about a concept, we go through an example. Okay, the rate of television thefts is doubling every 4 months. Determine to 2 decimal places the base b for an exponential model y equals a times b to the t of the rate of television thefts as a function of time t in months. Okay, so remember we have, this is our model. So just writing that down so we know where to start. We know that here it says the rate of television thefts is doubling every 4 months. Okay, determine to 2 decimal places the base b for an exponential model of the rate of television thefts as a function of time in months. So we know that this is y is 2a, right? Because it's doubling. So 2a is equal to a times b to the t. And what's t? T is your time. The doubling every 4 months. So t is 4. Okay? So ab to the 4th. Well, that means our a's cancel because we can divide both sides by a. And that gives us 2 is equal to b to the 4th. Or we can solve this by applying the 4th root to both sides to get b is equal to the 4th root of 2, or remember that's an understood 1 here, so we can rewrite that as 2 raised to the 1 divided by 4, and you can enter that into your calculators. And since we are going to 2 decimal places, that's approximately 1.19. 1.19. There you go. That's a little better. Okay, so that's B. Okay, so we get B is equal to 1.19. Now, in part B of this example, we want to find the tripling time to the nearest tenth of a month. So now our time is tripling. So instead of 2a, we're going to have, guess what? 3a. So we get 3a is equal to a, but we found b already. B was 1.19 raised to the t. Okay, so we're finding the tripling time, which means we're finding t using our model we came up with in part A. So this means our a's cancel because we can divide both sides by a, and that gives us 3 is equal to 1.19 raised to the t. But now that t is stuck in the exponent, we have to figure out how to get it down. You apply the log to both sides, the common log or the natural log, whichever one makes you happy. So we're going to do the natural log of 3 is equal to the natural log of 1.19 raised to the t. And now using our properties of logarithms, we can bring that t down front. So that's t times the natural log of 1.19. That's just a number. So we can divide both sides by that number, like so. And we get t is equal to the natural log of 3 divided by the natural log of 1.19. And that's approximately 6.3, but remember the time is in months. Okay, so t is about 6.3 months. Wavy equals means approximately. Okay, that's logarithmic functions and models.